here we go. Okay, so good. So for this last question, I think it's going to be a blast from the past where we have to use a sample size calculation. So if you go to your formula sheet, right, because, and these are all kind of from last day, so fresh start here. This is our sample size calculation, right? And so, because I think what they're saying is use a sigma of 250, right? Or it's probably a variable number, right? And so you want to find how large of a sample should she collect. And so you're calculating sample sizes. And so that's why I want to say that this is the one that you want to use. So what I'm going to be doing is, for my notes, I'm going to do chapter 8, part 1, part 2, and just keep adding to the same notes. So here, these are the notes from last day. So, I mean, at the end of chapter 8, you'll have all of the notes in one file, which is a little bit confusing, I guess, but then you can just kind of get rid of the old notes, I guess, and just have the newest version. And so for assignment 8, number, can't really say just the last one, number 6. Number 6, it's a sample size calculation. Sample size calculation, so I guess, which means you're going to use n is z star, so whatever confidence level you want, times sigma over the margin of error squared, right? And just remember that m is the margin of error. Right. Just double check here on the formula sheet. Z star sigma over, yeah, good. Okay. So, okay. So I think that's the one that you're going to use. And then the Z star, right, I'll use the little pointer. The Z star is going to vary depending on if you want a 95 or a 90 or 99% confidence interval, right? But the sigma is going to be the same for each of them. I'm pretty sure they said they want a margin of error of, well, here they want 25 points. That could change depending on the question, I think. Like some of these numbers are variable. Sorry, I don't have a pointer on this screen, but so some of them might be different from the one I'm showing, but pretty sure that's the one. So like I said, if you're having troubles with question 1, then let me know, but I don't know why it's being fussy for some and not for others, but yeah. Okay. So let me just check my chats here. I think we're all good. Cool. Okay. So today we're gonna, oops. Oh, your test twos, yeah. So I'm working on marking my calculus tests right now, and then I think you guys are up next. But I had 4 tests last week, so they all have to get marked. So they're coming, but you'll have to be a little bit patient, I guess. But I am working on them. So, well, I haven't started on them yet, but I'm marking tests. All right. So what we're going to do today, yeah, sounds good. Okay, cool. So today we're going to start talking about 2 samples. So I guess I shouldn't say today yet. Let's start with a little bit of review, right? And so for review, right, we've talked about one sample problems, right? So things like you collect a sample of manatees, let's say, right? So you're just collecting one sample, right? And then usually what we do is we want to, we've been doing hypothesis testing and confidence intervals. And so we do hypothesis testing. Right? Where we compare the mean, compare the sample mean to a value, right? The hypothesized mean. Yeah. Or for confidence intervals, we build an interval around one mean. Build an interval around X bar to capture mu, right? The population mean. So that's what we've been doing so far. But this idea of, so taking a sample mean and comparing it to some value, that's pretty limited, right? So usually what we do is we want to take two samples and compare those two samples. And so today, well, and I guess we talked about we had two types of questions that we have seen so far. Right, we said one sample mean sigma known, right? That's when we use Z and Z star. And then we had one sample mean sigma unknown. Whoops, there. Sigma unknown, which is the one that we did last day, where we used T's. T's require degrees of freedom, right? But besides that, nothing really changes, right? So now we're using T's instead of Z's. So today, here's where I wanted to start. So today, we start looking at comparing two samples. So two samples can happen. Let me just add another page here. Two samples can happen in two different ways. Okay. The first way is if the two samples are paired, right? So if the two samples are paired, okay, what this means is that we've got two observations from the same individual. Okay. So these are things like pre and post scores, right? So you write a pre-test and then you write a post-test to see if you've improved, or you know, you take a some sort of measurement before using a drug and then after using it to see if your symptoms have improved, that kind of thing. So a pre-post scores is a pretty standard paired situation, right? So often we call these paired samples t-tests or paired t-tests. Yeah. They can be called matched pairs, right? All these mean the same thing, but we're hinting at that we've got a pair of observations. And so what we want to do is we want to capture just the fact that we've made measurements on the same person. Right? There are even instances where we would use pairs even if it's not from the same person, but they're very similar. So even sometimes we argue that twins can be used as pairs, that kind of thing. And so if our two samples are paired, we want to capture that in our calculations. So what we do is we calculate the differences. And so imagine, so to do that, we calculate the differences, we calculate and analyze the differences. Okay. And so if you've got a pre-score here and then a post-score here, right? So first score I got was 4, and then after whatever treatment I scored a 6, and then this person started at 15, but still increased to 16. This person started at 1, and then went to 4. This person started at 3 and went to 7, that kind of thing. So this is all here. Maybe I'll just use just shorthand. So ID, right? This is person 1, 2, 3, and 4. Okay. Person 1, right, started at 4 and increased to 6. Person 2 started way higher and increased to 16. So if we treated these samples as if they were independent, which is the second option, kind of spoiler alert, then we wouldn't be able to capture the fact that 4 went to 6, 15 went to 16, 1 went to 4, and 3 went to 7, right? Those differences would be kind of lost, right? So what we're trying to capture is we're trying to capture the fact that this person, even though they started low, they still increased, right? So regardless of where you started, you increased. And so it doesn't really matter where you started from, right? And so what we do is we calculate the difference. And it doesn't actually matter which order you calculate the difference in. Let's do pre minus post because it's easier to see. So 4 minus 6. Okay, fine, whatever. Why am I hesitating? Any takers? Well, because I don't want to have a difference of -2 when it looks like it's an increase, right? So maybe what I should be doing is I should, like I said, it doesn't matter as long as you're consistent, then let's do post minus pre. So 6 minus 4, 2, 16 minus 15 is 1, 4 minus 1 is 3, 7 minus 3 is 4. Right? And so here, because of how we've done it, right, a positive difference means there was an increase from pre to post, right? Whatever the treatment was, kind of the before and after results. What if I scoot this down just one, or just, you can think about another observation. What if I add ID number 5? And they started at, oh, that'll get too confusing. They started at 6, and then they went to 6 here. And this is going to be the key part, or the key idea behind this whole thing. That's a difference of 0, right? And so what we're doing is, when we've got these paired samples, what we're doing is, now I've summarized everything that happened over here in the pre-post scores. I've summarized all this activity in one sample of the differences, right? And so now you can imagine just ignoring the rest of all this here, and only focusing our analysis on the differences, right? And so now we can, we are back to a one sample problem, but it is one sample of differences. One sample of differences. Okay. And so that's going to be the key to what we're doing here, right? And so instead of comparing the mean of these differences to some number, that number is always going to be 0, right? Because we want to assume that there's no change from pre to post, meaning that the difference would be 0, right? And so that's going to be the key to what we're doing here. And then, just as a little kind of appetizer, because I think I said I was going to do, oh yeah, the second way that we can have 2 samples is if we actually have 2 independent samples, right? And so there is no natural way to link one observation in one group to another. There is no natural way to link an observation in sample 1 to an observation in sample 2, right? Because that would put us at a paired test. And honestly, most likely, you know, out in real life, you're going to be working with 2 independent samples, right? And so you're going to compare, you know, the speed of manatees to the speed of otters or something like that, right? And so now you're working with 2 independent samples. And what's kind of fun is, we'll get there next day, but we do not, we do not need the 2 samples to even have the same sample size. So we do not need the 2 samples to have the same sample size, which to me is kind of cool. But we'll get there. So this is section 8.3. And of course, the paired is one we're doing today, so that's in section 8.2. All right, but the ideas stay the same, right? And what we're gonna do for all of these is we're gonna introduce, sorry, now there's all that blank space. Oh, and remember, I didn't change the numbering, but it's okay. So you've got your, and this everything here kind of goes through what we did, but we'll go through and do a hypothesis test, and I'll outline things that are going to be different for a paired samples t-test. But I would say probably the hardest part is figuring out when you have paired samples, right? And so now, right, we've got 3 types of questions that we could choose from. And the most important thing, especially if you look at your formula sheet, the most important thing is going to be to figure out what type of question you have, right? Because here we've talked about, if we just focus on our hypothesis testing section, that's the first type we talked about. And then the second type we talked about last day was with one sample sigma known. Here, this is where we are today, is for the paired samples, third type. And then next day, the fourth type for means is for the independent samples, right? So we'll just kind of work our way through these. Notice that we've still got the null hypothesis, and it's a little bit different, right? Because it's got the mu, but it's got a subscript d, and that's for the differences, right? Because we're analyzing the differences equals 0. But then our t, if you just ignore the subscript d's for a bit, right? The t looks the same as it did up here, right? And we'll kind of dissect why is it only x bar up there? Well, because that's your mu naught, which is 0 always. And then your degrees of freedom is still going to be your n minus 1. So, all right. So we kind of did that pre-talk. So what we're going to do, right, is our null hypothesis is always going to be the mu d. So d is for differences, right? And we always compare it to 0, right? Because a difference of 0 means no change, right? And so we always want to test the hypothesis. The null hypothesis is always going to be a statement of no change. So a difference of 0, that's what you're comparing to. And then if you find that the mean difference is different from 0, right, either it's less than or greater than 0 or just significantly different from 0, well, then that's your alternative hypothesis, right? That proves that there's a difference in the 2 groups, okay, or at least in the 2 measurements. And so this is always your null hypothesis. So for paired tests, H naught is the mean difference. So mu subscript d equals 0 is always the null hypothesis, right? Your H naught. And so what's nice here is you don't have to figure out what number to compare things to. This is always going to be your null hypothesis, right? So as soon as you've decided that, oh, I've got a paired samples test here, right? This is your null hypothesis. Whereas before, right, we had to try to figure out what number goes here, and that can be tricky, right? And so, so what's nice about paired tests is that this is always going to be your null hypothesis. It's a little bit trickier talking about your alternative hypothesis. Usually, to be nice, I make it a two-sided test, right? Because otherwise you have to figure out if mu should be less than 0 or greater than 0. And we'll talk about that in our examples. Okay. So then if we go on to the next part, right, our next step is to do the test. And so usually, right, if we're doing a t-test for one sample because we've boiled it down to one sample of differences, so then we would use the average of the differences, so the sample average, and then minus the mean of the differences, but we just established that that's going to be 0, right? And so we've got that little blurb here, and so that's why on your formula sheet, this is what's on your formula sheet. Right. I think on the formula sheet, only has n, right? But it should be nd, which is the number of differences, right? So it gets confusing because, right, you've got all those pre-post scores, and so n is the sample size of the differences, right? And then same thing for your degrees of freedom, right? Because now we've got a t here, so we need to find the degrees of freedom. And so n is the number of the differences minus 1. After that, once we've got our p-value, right, from our t-table, then you draw your conclusion the exact same way, right? If the p-value is less than the alpha level, then you have enough evidence to reject H0 in favor of HA. Okay. Any questions before we do an example? And let me just check here because it actually doesn't show me. Okay. Good. All right. So in example 5, so we've got 200 observations were randomly sampled from a survey called High School and Beyond. The same students, right? So the same students took a reading and writing test, and their scores are shown here. Okay. And so this is the high school and beyond, I don't know, 2 data, doesn't matter. So we have 200 students, and they each have some ID number. That one doesn't matter. We don't really care about that. But then they got their reading score and their writing score. Okay. But because we're measuring the same individual twice, right, we have to take that into account, right? So imagine you're running, you're training a bunch of runners, right? And so a fast runner, right, would start at a high score, and then, well, now this one's a decrease, so it doesn't really help, but right, they would start fast, and then even if they increase their speed, right, they would be way faster than anyone who started out as slow, right? And these are kind of moving the other way, so it doesn't really help, but the idea is the same, right? And so if you start slow and then you increase your speed, you're still going to be a slow runner, but you're going to be faster than you were at the beginning, right? And so that's the difference that we want to catch, right? And so that's why we have to use paired data. And so first thing we want to know is, well, is this paired data? And then we'll compare the distributions. We'll talk quickly about the assumptions. I'm not too concerned about the assumptions, but we should talk about them. And then finally, in part D, we'll do a hypothesis test. So do these data provide convincing evidence as soon as you need evidence for something? Right? This is a hypothesis test. So it looks kind of easy and whatever, but it's actually a huge question, right? Do these data provide convincing evidence of a difference between the scores on the two exams? Okay. So, and then suppose we were to construct a 95% confidence interval for the average difference between the reading and writing scores, and then based off of part D, would you expect this interval to include 0, right? And so let's go ahead and do that. Thank you. So first thing we're going to do, right, is we're going to just argue that this is paired data because we've got 2 observations on the same individual. And so you would just argue it this way. It's not something that I would get you to do. I would never get you to argue it. But you do have to read a bunch of questions and be able to figure out what type of question it is, right? Because I won't tell you which type it is. So, and then once you decide on what type it is, then figuring out which formulas to use is easy, right? But if you use the wrong type, for example, then all your analyses will be wrong, right? So that's bad. So you want to get really comfortable with figuring out what type of problem you have. Okay. Oh yeah, so we've decided we've got paired data, and then what we want to do is I've shown the side-by-side box plots. You guys can just ignore the R code here. You don't have to do that or use that. So, but it's good to have seen it. I don't know, it doesn't hurt. So the reading scores, right, have a little bit more spread, a slightly lower median than the writing scores. The writing scores have less spread, but a slightly higher median, right? And so we'll see what that means in terms of if there's a difference in the scores or not. Just looking at this, I don't think that there's a major difference in these scores, right? These look very similar, just kind of overall. There's not, now this is where I wish I could show you my fingers, but if this was kind of shifted down a bit, then I would start being suspicious and saying maybe the writing scores are lower than the reading scores. But it's not that strange to think that the reading and the writing scores would be pretty similar. So let's see. So the first thing we're going to do is we're going to calculate the differences, right? So for each of these reading and writing scores, we're going to calculate a new column over here of the differences, right? And just subtract one from the other. Like I said, the order that we subtract in does not matter as long as you're consistent all the way down. And you're not going to be calculating the differences anyways, right? You would be given the differences and probably the mean of the differences and the standard deviation of the differences, but this is just a big run through. So if we look at the histogram of the differences, I would say they follow a normal distribution, which is nice, right? Centered on 0, it looks like-ish, right? One thing that we haven't really talked about and that I'll probably save talking more about until we talk about proportions, but one way to make sure that we have independent observations, because that is one of the assumptions, is to make sure that our sample size is less than, and I know that's counterintuitive, less than 10% of the population, right? And so observations can be assumed or can, just go with it. You'll probably be able to word it better than I can, but observations can be assumed to be independent. Not sure what happened there. If we have sampled less than 10% of the population. Okay. This is one of those kind of assumptions that we check. Even if it's not true, we still keep going and then we just mention that there's a higher chance that our observations are not independent, but it's hard to check too, right? Because unless you know the population size, then you would just be arguing that it's reasonable to think that it's less than 10% of the population. So I'm going to leave that more for when we test proportions, which is in chapter 9. Okay. And then one of the other assumptions is that the distribution looks approximately normal, right? And so those are our two assumptions. So what we do is we calculate the mean of the differences. So this is the mean of the differences. And this is the standard deviation of the differences. And once you kind of get over how scary this looks, then you can kind of decipher it, right? The mean of the data and the differences is negative 0.545, right? So let's see here. How did we calculate these differences? We did read minus the write. So let's just remember that the differences, the difference is the read minus the writing score, right? The reason I care about that is because we've got a negative difference here, right? And so what does that tell me? It tells me that on average, the writing scores are higher than the reading scores, right? Because that's how I get a negative value. Okay, so since x bar of the differences, and I'll put a little subscript d, right, is negative, we know the writing scores, are higher than the reading scores on average, right? We just wanted to know if there's a difference, but this is where we would have to go to if we wanted to do a one-sided test, right? If I want to know if the reading scores are higher than the writing scores, then I would want to know, well, how does that reflect? How is that reflected in the mean, right? Does it give me a positive mean or a negative mean? So, like I said, right, our null hypothesis is always the same. So once you've decided that you've got a paired problem, like a matched pairs or paired samples t-test, doesn't matter what you call it, then this is always your null hypothesis, right? Here, we're using not equal to because we want to know if there's a difference. Want to know if there is a difference in the scores. So it gets kind of confusing here, right? Because we're talking about the mean difference being different from 0, right? And so here, this difference is of course completely separate from the mean of the differences. So the words here can get a little bit jumbled, but you just have to stay on top of it, right? So the mean of the differences is different from 0. Right, so what we're saying here is the mean of the differences is different from 0. Right, that's what we're saying here. Because I've got that not equal to, right, I've got a two-sided test. And you'll see that the two-sided test is actually easier to deal with if we've got matched pairs. So that's why we're starting with that. And then the next example is a one-sided test. But then once we have the mean of the differences, the standard deviation of the differences, the sample size of the differences, then we can just go through and we can calculate and remember 3 decimal places for t's to match the t-table. So what do we do with this t, right, that we've calculated? Now we use the t-table. Oh yeah, but I guess we could say here, looking at this, right, again, as always, if it's larger than 2 plus or minus 2, then we would suspect that we're going to reject the null hypothesis. Here, I don't think that there is a difference because it's so small, our t is so small, but we're going to use the p-value just to make sure. So what we do, right, to use the t-table, we need our degrees of freedom. Degrees of freedom is n minus 1, which is 200 minus 1, so 199. But if we go to our t-table, what we'll find is, probably clean this up a little bit. There. If we go and try to find, oh, weird. It's not letting me, okay, that's weird. If we go and we try to find 199 degrees of freedom, we're choosing between 100 and 1,000, right? But remember, the rule is that we always have to round down because otherwise you're assuming you have a larger sample size than you actually do. So you have to round down. So that's why we say that we're using 100 degrees of freedom. And what we do is we go along here. So now we're stuck on this row here. And what we do is we try to find 2 values, or the 2 values, that wrap around negative 0.867. But remember, we don't have negative numbers, so we're just at 0.867. So that's between this value and this value. So then we've got a two-sided test, right? And so we trace down here, and then remember to read it from right to left. Right, because 0.3 is less than 0.4. So what we do, right, is we always set up our little p-value blurb the same way. As soon as we're using the t-table, this is what we have to say. And all of this, none of this is optional, right? So we have to say using the t-table with this many degrees of freedom. And then if you can't find that number, you'll say, but using whatever you decide to use. We find that the calculated t, and we wrap it up in the absolute value signs because that's how we drop the negative. The absolute value of t is between 0.845 and 1.042, which means that our two-sided p-value is somewhere between 0.3 and 0.4. Okay? And so here, right, both of these are larger than 0.05. So even though I've only got a range, I know my two-sided p-value is somewhere in here, and I can still use that to draw my conclusion. Okay. So what it looks like, oh yeah, so here, okay. I was wondering where the 0.545 came from, but it's our sample mean, of course. So here, the two sample p-value is the probability of having a mean that's more extreme than plus or minus 0.545. So here's our actual mean. We found a negative value, but because we're doing a two-sided test, we're pretending it could happen over here on the positive side, and then the values more extreme than that are in the tails, right? So this is why we call it a two-sided p-value, because I care about both tails. But the t-table is nice because it's already taken that into account, right? It's found the area in both tails. So our conclusion, so since our two-sided p-value is between 0.3 and 0.4, it's not less than our assumed alpha level of 0.05, right? Which means we do not have enough evidence to reject H0. So our p-value is not small enough, not smaller than 0.05, so you do not have enough evidence to reject H0, right? It's still so important that we do our conclusion in terms of H0. This means that the data do not provide convincing evidence of a difference between the scores on the two exams, right? The reading and the writing scores. Okay. And so remember, everything in these grayed out boxes, that's everything that I need to see for a complete answer, right? Everything that's outside, that's just me talking around it, trying to explain everything that's going on in between, right? But everything that you need to say for full marks, they're all in these boxes. Okay? The last question, right, was something along the lines of, if you made a confidence interval, yeah, so suppose we were to construct a 95% confidence interval for the average difference between the reading and writing scores, would you expect this interval to include 0? So we can construct a confidence interval. If you go to your formula sheet for paired data, there isn't even one on here, right? Because it's back to the one sample mean sigma unknown case, right? And so we don't even really need a separate formula for it. It's just that x bar would be x bar of the differences, and then s is the standard deviation of the differences, and n is the sample size of the differences. Right? And so if we made a confidence interval, would we expect the interval to include 0? So going back to what we did here. So we didn't have enough evidence to reject H0. Remember that H0 is that the mean difference is 0, right? So now we're saying, okay, well, I don't have enough evidence against this, so this must be, I'm going to assume that this is true. So if I make a confidence interval, I would expect 0 to be in that interval. Remember we talked about using confidence intervals in as a form of hypothesis testing. So if the hypothesized value is in the interval, right, then you can't reject the null hypothesis. Failing to reject H0 means the hypothesized value, and this can go both ways, means the hypothesized value is in the confidence interval. Can I just write CI there? Is in the confidence interval. So that's what the answer is saying. So if we were to construct a 95% confidence interval for the average difference between the reading and the writing scores, we would expect this interval to include 0, right? As our two-sided hypothesis test at the alpha equals 0.05 level concluded the population mean was not significantly different from 0, right? So 0 must be in that interval. Right? And then you guys can ignore the R code here, or use it, I don't know, doesn't matter. You just have to tell it which two samples you want and make sure that you tell it that paired is true, so it treats them as pairs. It calculates a more kind of specific t, but also a more specific p-value, right? Because it's able to use the actual degrees of freedom, whereas our table is limited. Okay. It also gives us a 95% confidence interval, right? Going from a negative number to a positive number, so 0 is in here. 0 is included in the interval. Okay. This is just a note for if you're using R, which we're not doing, so don't worry about that. Check for questions here. See none. Let me just check over here. Good. Okay. I think, what time is it? 11:52. These time zones are driving me crazy. I think I have about 30 minutes left. Yeah, cool. Okay. Good. So there is an example, right? And maybe what we'll do is we'll come back to it, and if we don't have time to do it completely, then I'll post the rest of the solutions just like I did last day. And so, because I want to show you guys an example of a confidence interval too before we go. So I'll leave some room. I'll add some room in there if we get to it. Yeah. So the confidence interval, right, is not even on your formula sheet, right? And so there's no specific formula, which I think is an oversight, actually. I think it was meant to be on there, but they forgot it. No specific formula on your formula sheet. Right? But we just use the one for a one sample mean, sigma unknown, our one sample is the sample of differences. It's the sample of differences, right? So X bar is the sample mean of the differences. S is the standard deviation of the differences. N is the sample size of the differences. And then, of course, the degrees of freedom is the sample size of the differences minus 1. So let's go through this example 7 together. And so an agricultural field trial compares the yield of 2 varieties of tomatoes for commercial use. The researchers divide in half each of 10 small plots of land in different locations and plant each tomato variety on one half of each plot. After harvest, they compare the yields in pounds per plant at each location. The 10 differences, which we're just using variety A minus variety B, right? So now we've got 10 differences, give the following statistics, right? So the mean here, this is the mean of the differences, right? So that's important. And the standard deviation of the differences is 1.23. So this kind of blurb is how you're going to be given the information most likely, right? And so I tell you that it's going to be differences, how the differences were calculated, and then I don't even have to tell you that it's for the differences, right? I can just tell you that the X bar is this and the standard deviation is 1.23. is there convincing evidence that variety A has a higher mean, has a higher mean yield, right? Higher than variety B. Construct a 99% confidence interval for the mean difference in the yield of variety A and variety B to answer the question. So one thing to keep in mind, right, is that the difference is A minus B. Okay? So if variety A has a higher yield, right, then the difference would have to be positive. Right? So if A is higher than B, right, the difference must be positive. Right? And you can try it, right? So if I let A be 2 and B be 1, then the difference is 2 minus 1, which is 1, which is positive. Right? So you can do a spot check, right? But I would say that this kind of figuring out how the differences behave, if they're going to be positive or negative, right? That's going to be the hardest part of a paired t-test. Okay? Otherwise, it's just a one sample t-test with nothing else going on. Right? So again, everything that you need for full marks are in these boxes. So everything in here, you have to show me blah, blah, blah. So using the t-table with n-1 degrees of freedom, so 10 minus 1, so 9 degrees of freedom, which is actually on our table, right? We find t star is 3.250, and we'll just confirm that for a confidence level of 99%. So if we go to our table, oh, which I had completely forgotten to post a table on your Moodle, but now it's up there at the top of the Moodle page. So we've got 9 degrees of freedom. So this, we can't stray from this line. And we want a 99% confidence interval. So our t star is 3.250. So that's good. So that's the one that we have here. So that's good. And then we use just the regular setup, right? Keeping in mind that the mean is the mean of the differences. 3.25 is our critical value, right? Our t star. S is the standard deviation of the differences, and n is the number of differences. So once you go ahead, calculate this, right, we get a confidence interval from negative 0.714 to 1.814. We use the same blurb always for interpreting any confidence interval. So we're 99% confident that the interval from the lower end to the upper end, so negative 0.714 to 1.814, captures the mean difference in yield of variety A and variety B. Okay. Since a difference of 0 is within this interval, right? Difference of 0 means that there's no difference between A and B, is within this interval, we do not have convincing evidence that variety A has a higher mean yield. Right? So this is a way that we could build a confidence interval and do kind of a quick hypothesis test on top of it. There's also another example, a confidence interval example, but I want to use this time because the next section is the 2 independent samples, which we'll do next day. But I want to go back and actually do the hypothesis testing one, and then I'll post the solutions to this one if we don't have time. So, where were we? Here, Jocko's garage. So funny to say. Okay. So insurance adjusters are concerned about the high estimates they're receiving from Jocko's garage. Sounds suspect. To see if the estimates are unreasonably high, each of 10 damaged cars was taken to Jocko's and to a trusted garage, and the estimates were recorded. Okay. Is there evidence that Jocko's estimates are significantly higher than the estimates from the trusted garage? Okay. And so what we do is, oh man, I used to have the differences here. Eek. Well, is there evidence that Jocko's estimates are significantly higher than the estimates? Oh yeah, okay. So this one, it used to be all kind of hard, but now I've made it a little bit easier. So significantly higher than the estimates from the trusted garage. Oh. Sorry guys. Seems we're having a, I think it's building wide. Okay, weird. Sorry guys. Just a little fire drill, I guess. Oof. Yeah. Okay. Where was I? Okay. Yikes. So we want to know if Jocko's estimates are significantly higher than the estimates from the trusted garage. So if we have a look at the actual data, right, car number 1 doesn't seem to have that much damage, right? Jocko's estimating that it's going to take 500 to fix it. The trusted garage is estimating that it's going to take 430 to fix it. Jocko's estimate is higher than 430, right? But what we want to know is if it's consistently higher for all of these cars, right? And we're finding some estimates where Jocko's estimate is actually lower than the trusted garage, kind of working against that. So we'll see here, but right, so what we want to do, right, is we want to capture the fact that car number 1 had way less damage than car number 2, right? And so we're capturing these paired differences, right? So the first part here is asking, is this paired data? Let's say I'll add a page here, fresh page. So part A, this is paired data. Since we have 2 measurements, 2 measurements on each car. We're going to calculate the differences, and we're asked to use the difference is Jocko minus the trusted. So here I'm going to find the difference. Jocko minus the trusted. And I wish I had the other. Okay, here we go. 500 minus 430. I feel like this is a bit of a waste. I have these numbers somewhere. Haha, I found it. Looks like I wasn't that mean after all. The mean of the difference is 80, and the standard deviation of the difference is 84.59052. So, okay, so what we would do, but then we would have the mean here is 80, mean of the differences is 80, and then we're told that the standard deviation of the differences is 84.59052. Okay. A lot of people usually get hung up on the fact that, okay, well, the differences here translates to 80, right, but not the differences here for the standard deviations. And that's just how we calculate the standard deviations. They don't translate that way, right? So we have to calculate these individually. So it might be good to just do a little refresher, calculate all these differences, find their mean, find their standard deviation, right? But they're given, so we'll pretend that we did step B, and I'll put it down here. B, pretend we did it. Part C, set up the null and alternative hypotheses, right? And so like we said, the sign in the alternative hypothesis, we're gonna need to pay attention to it because we want it to know if the Jocko's estimates, or if Jocko's estimates are significantly higher, right? And so one clue is if you pick an example of 500, that's higher than 430. 500 minus 430, if we calculate the differences the way that we were asked to, we get a positive difference, right? And so here, we want to know if Jocko's estimates are higher than the trusted garage. Right, and so just remember how we calculated the differences was Jocko's minus trusted. And just as an example, we said 500 minus 430 is 70, right? This is positive. Okay. So our alternative hypothesis must be that mu d is greater than 0, right? Because this is positive. And we always want to compare it to 0, right? Because our null hypothesis is going to be in terms of 0, right? And so our null hypothesis is always mu d equals 0, right? That's always the case for paired tests. And our alternative hypothesis is that mu d is greater than 0. Remembering that these values and these values have to be the same always, right? So the only thing that's changing is the sign here. So that's why we have to compare the mean difference. Is it greater than, less than, or just not equal to 0, right? And so figuring out a one-sided test for a paired t-test is hard, but we did it. One-sided test. So I need a one-sided p-value later on. Okay, it's kind of breaking it down to step by step here. So part D is find the test statistic. So dt is x bar d over the standard deviation of the differences over the square root of the number of the differences, right? Technically, minus 0 from up here, but we just drop that because it'll always be 0, so we just ignore it. So in our case, we've got 80 over, and now I can't remember what it was. It was a huge number, or long number, 84.59. How about we just use 84.59? I'm cheating. If I give you all those decimal places, I want you to use them all. But just for me to speed things up a little bit here, 84.59 divided by the square root of 10. 84.59 divided by the square root of 10, I get t is 80 divided by 26.74970,673. 80 divided by that guy I get a t of 2.990686994. With a t that large, I already suspect I'm going to be able to reject the null hypothesis, right? Because it's larger than 2. But we'll just confirm. So, part E, find the p-value. So what we do, right, is we calculate, we use t to 3 decimal places, 2.991. And our usual blurb using the t-table with degrees of freedom equal to n, and I'll just use a subscript d, you don't have to, n minus 1 is 10 minus 1, which is 9. I do want to see all this written out though. I want you to show me that you know what you're doing. So we have 9 degrees of freedom. We find, and then I use the same setup always. I put my calculated t in the center of the page in absolute value brackets. Here it's positive, so I don't really need them, but I just always use the same layout for all my problems. And with 9 degrees of freedom, we want to figure out what values wrap around 2.991. So we go to our table. Oops. And what we do, 2.991, so we already found 9 degrees of freedom here. 2.991 is somewhere between 2.821 and 3.250. So I'm going to write those down. Lost it. 2.821. Oops. 2.821 and 3.250. Right. And then I say, which means, and then just remember that we want a one-sided p-value here. So I write one-sided p-value. Again, in the center of the page is between 2 values. And if I go to my table, right, I trace down to my one-sided p-value and trace down to my other one-sided p-value. And making sure that I write them from right to left, right, because they're increasing as I move to the left. 0.005, oops. So now I'm between 0.005, 0.01. I'm pretty sure, let me just check. Yeah. So here's our p-value, right? And so we have to write all of this for full marks. Right? But like I said, as long as you use the same setup, so you write your calculated t in the center of the page, figure out what values wrap around it in your t-table, and then just drag down. Remember, this 2.82 actually matches this p-value, and 3.25 actually matches this p-value, right? But I like to have the inequalities matching because I have a harder time with that. Okay. So the last part, what can you conclude? So here's our conclusion. Is there evidence that Jocko's estimates are significantly higher than the estimates from the trusted garage? I dare say yes. F, our conclusion. Remember, we use the same blurb always, right? And so we say we have to compare our p-value to our alpha level. I don't remember them telling me an alpha level, so I'm just going to use 0.05. So since our one-sided p-value is between 0.005 and 0.01. Both of these, right, are less than 0.05. In fact, we only need to check the upper bound. If it's less than 0.05, then this will definitely be less than 0.05, right? It is less than our assumed alpha level of 0.05, which means, so now we're on to the second part of our conclusion. What does that mean in terms of the null hypothesis? Which means we have enough evidence to reject H0 in favor of HA. What does that mean? So now we're on to the third part of our conclusion. What does that mean in terms of the actual question? We just reword the question as an answer. Is there evidence that Jocko's estimates are significantly higher than the estimates from the trusted garage? Here, I'll even, oops, steal it, copy, just so we can reword it. There is evidence that Jocko's estimates are significantly higher than the estimates from the trusted garage. And then I'll just put a little arrow here. Reword as a conclusion. This is what we did there. Nice. And that's it. So the actual calculations and how we went through and did it, right? Our T stays the same. It's just the idea of where the data came from, right? That we have paired data that we have to deal with. But otherwise, everything stayed the same. So what I'll do is I'll post the solutions to example 8 before I post the notes. So I'll add those on there and then I'll post the notes. And then next day we'll be all set to do section 8.3 in our textbook, but I have it as 5.4. All right, neat. Any questions before? Let's see here. Are there any updates regarding the lab exam? Okay, so the lab exam is, we're still kind of, sounds like me cooking. Yeah. So the lab exam, we're still working on it. Once we have finalized on what we're gonna do for it, then I'll let you guys know. But it'll look a lot like the multiple choice that you did on test 1, right? And so I'll just kind of put it in here, but it will look a lot like the multiple choice, the multiple choice on test 1. Bless you. Cool, awesome. But like I said, don't worry about those until we've got it all figured out. But it will be a lot of, you know, kind of definitions and just kind of test 1 multiple choice style. All right. Any others? All good. All right. Well, I won't see you, but It would probably be through Moodle, but like I said, we're just kind of figuring out how to do it as a group, so probably. Probably through Moodle. Okay. All right. Nice. Okay. I'll stop this recording here.